So, as people are coming in, I guess most people probably should be here for this, but you guys have earned the right to decide the fate of this class. We have two options really. There's 52 spotlights, so we can't really do them in one lecture. They're going to require 2 lectures. If we have you guys do one lecture, we have less than a minute each for the spotlight. I mean, so less than 2 minutes each, which would be really short. So it's probably better to do the spotlights over 2 lectures. So the 2 options are, next week we have the last week of lectures. We do like 1 bootstrap lecture and then 1 Tice-League lecture, which would be kind of fast. And then the following week we do spotlights for both days. That's option 1. Option 2 is that we spend next week on bootstrap. We spend the following week on Tice-League, and there are no spotlights. So the spotlights, they're just there because I think they're fun. I mean, you're not really graded on them. In fact, we don't grade them at all. It's your project, like submissions that we grade. So how many people prefer option 1, which was 1 week of classes and 1 week of spotlights? Okay, Jizu counts as 80 people, so. All right, so I guess. Okay, how many people prefer option 2? Is this because you feel like you have less work without the spotlights? Or do you actually want to hear us lecture? Option 1 is less work. Okay, so let's get started with the last sparsity lecture, and then next week, like I said, we'll do bootstrap, and then I guess we'll take the whole week, and then the following week we'll do Tice-League. So I just wrote down a board to remind you where we ended up last time. We ended up with a few more facts than this, but we're gonna go through in some detail a pretty basic result for the lasso, but that just comes right out of the KKT conditions. So it's a nice example of how you use them. Another plan is to talk about some theory for the lasso, and to go through in detail one such theoretical statement. And then if we have time, I might talk a bit about bars, which is a path algorithm used to fit the lasso. It's kind of interesting, but we'll have to see whether we have time for that. So, all right, so here's where we kind of got to last time, plus a bit more. We talked about this lasso problem and how it provides for us a form of regularization in the linear model. And by the way, pretty much all the theory we discussed, essentially all the theory we discussed, with a few minor exceptions, is going to carry over to a setting in which I replace this least squares loss by a smooth, strictly convex function. So strictly convex, say in the fitted value x beta. So it could be like logistic regression loss, it could be like a Poisson regression loss, we could be doing a generalized linear model, L1 generalized linear model, etc. So it's a lot more general than just the linear model, although it's just kind of easiest to work in the linear model setting. Okay, so this idea of regularization and variable selection would be the one norm extends beyond the linear model definitely. And there's lots of theory that I could point you to. In fact, I gave a reference to a pretty recent book that you can look at that has theory for the lasso in the linear model setting as well as these more general settings. Okay, so like I said, regularization and variable selector, so it helps us both maybe with improved estimation accuracy as well as interpretation. And we just kind of rattled off a few facts from last time. The solution to this problem is not necessarily unique, which is not a good thing. That can happen if, for example, X has more columns than rows, if we're in a high dimensional setting, so we have more variables and observations. Because then this term is not strictly convex, and this term is not strictly convex either. So the entire thing is just plain convex. So it could have a non-unique solution. But the fitted value is always unique. We went through an argument with that last time. That's somewhat reassuring, although that's also true with just plain old linear regression in the high dimensional setting too. Okay, then we saw the KKT conditions, right? We've seen these a bunch of times. Looks like x transpose y minus x beta equals lambda times the subgradient of the one norm, evaluated at beta. So this is just taking the subgradient of this criterion instead of equal to 0. That's what we get. Okay, so S is going to be equal to the sign of the solution in the non-zero component and anything between -1 and 1 when the solution is 0 in that component. And so just from these set of conditions here, we saw that the subgradient is always unique. It's defined in terms of the fitted value, right? This is an equation that defines the subgradient in terms of the fitted value of x beta, which is always unique. And that implies the following nice property. If you give me two lossless solutions, beta hat and beta tilde, then where they're non-zero, they have to agree in sign. Right? Because where they're non-zero, the subgradient is uniquely determined by their sign, and the subgradient itself is unique. So they have to share signs on the overlap of their support. That means that we can't have this problem like we do in linear regression, where we return an estimate that has a conflicting sign with another estimate when it's non-zero. That's really bad for the sake of interpretation. The lasso never has that problem, even if the solution is non-linear. And we define this equicorrelation set, which ended up being a useful thing for us. It's a set of all variables j, such that the KKT condition is satisfied with s equal to plus or minus 1. It's just what happens when xj transpose y minus x beta is equal to lambda. And we think of this as a correlation between a variable, xj, and the residual from the lasso fit, y minus x beta hat. It's not always a correlation, right? If x doesn't have a mean 0 and standard deviation 1, then it's just an inner product. But we typically standardize the variables before running the lasso, so we can think of this like a correlation. Okay, so these are the variables that achieve the maximum correlation with the lasso residual. Okay, and then from there we just did a little bit of kind of word work, and we said that, well, we could also write the equicorrelation set as a set of all j for which the subgradient is equal to 1 in absolute value. And that means that the equicorrelation set is going to contain the support or the active set of any lasso solution. Right? Because outside the equicorrelation set, the subgradient has to be strictly less than 1, which means that any lasso solution has to be 0 at that component. And then we wrote the KKT conditions like this. We just rewrote the KKT conditions over the equicorrelation variables. We just looked at a subset of them, right? There's P conditions, and I just grabbed the ones that correspond to the variables that are in E. And I'm using the notation that I'm using last lecture, which is that this grabs columns of a matrix, and this just grabs components of a vector. And then I also noticed that here, right, because beta hat is 0 outside of E, I can write this matrix product as just xe times beta hat E. So now I have an equation, a linear equation in beta hat E, and I can solve it. So we did that, and it looked like this. After we just rearranged and solved the equation. Okay, where eta is in the null space of xe, and we also have to have the property that it delivers us an estimate whose sign is se, right? Because that was the subgradient over the equicorrelation variables, and so the sign has to agree with this. All right, so let's just take a look at that for a second. What we're saying is that any lasso solution must have this form. It must have the form. Think of E as indexing a set of kind of important variables, and we're going to do a regression over those important variables. This is like the regression coefficients. X transpose X is a pseudo-inverse, because it may not be invertible. X transpose Y minus a term that accounts for the shrinkage in those regression coefficients. It's like least squares adjusted by shrinkage, and there's not one solution, there's many. Any solution must have this form where this eta can be anything that lives in the null space of those correlation variables, and it must have the property that when we add it to this canonical solution, we retain the signs. That just came from rearranging the KKT conditions. Okay, so this is useful. It's kind of like a uniform representation for lots of solutions. And we also have theta hat minus e equals 0. Right? We said as well. But now we have the following important fact that we're going to work with right now, is that if we say the rank of xe is equal to the size of e, in other words, if the number of if the columns of this matrix are linearly independent, then its null space is just the set containing 0. Right? I can't take any linear combination of linearly independent vectors and make it 0 besides if I take the coefficients to be all 0. And therefore, there's only one option here, right? I can only choose one eta, that's 0. And this is also becomes an inverse because that's invertible, because it has full column, right? So the solution looks like this. Okay, so E, like I said, is a set of variables the lasso picks out for us, the variables that achieve the maximum correlation with the residual. If that set of important variables happens to be linearly independent, then there's only one lasso solution that looks like this. There's regression on those variables. To get the regression coefficients, it applies a bit of shrinkage. And it zeroes out the variables, the coefficients of the variables outside that set. Okay? So we're going to prove now that essentially this always is the case. It always is the case that the variables selected by the lasso are these active correlations that are linearly independent, and therefore the solution is pretty much always unique. And has this. And again, so just a very simple argument comes from the KKT conditions, but that ends up giving us a nice result. Yes?
So you for the ones that aren't 0, it's very close to the normal, ordinarily squares coefficients. I think I've heard some people advocate for once you do the lasso selection, then just taking only those variables and doing least squares. Do you have a comment on doing that or not?
Sure. Yeah. So the comment was, the comment was that what happens if we just take these variables and then I get rid of this term, and I consider that my new estimate. That's pretty common. That's sometimes called the relaxed lasso. I think it has its advantages and its disadvantages. So the advantage does that you're trying to eliminate bias, because if you really do have a set of variables E that are close to, say, the best predicting set of underlying variables in a linear model, or maybe the true model, if the true model is linear, then you're eliminating bias, right, because you're not shrinking. So that's the advantage. The disadvantage is that, not surprisingly, by doing so, you're adding extra variance to the estimate. So it can hurt a lot in certain situations, and it can help in other situations. So I think it's really depends on how strong the signal is in the problem. I generally would not advocate that as a general practice, because you don't really know what situation you're in any given situation. And so a lot of the tools we have for the lasso, they rely on the fact that it shrinks, and so we understand things about it. And then when we get rid of that, we don't really understand the properties of that estimator as well. But yeah, certainly it's common. Yeah, at the end, so now that we've canceled the spotlights, I'll cover Stein's lemma, and then I'll use Stein's lemma to derive an estimate of degrees of freedom for the lasso, or exactly derive actually a quantity which we call degrees of freedom and the effective number of parameters that the lasso uses. And we'll see that actually having the shrinkage here is very important. If we got rid of that, then we wouldn't know what the answer was. Good question, though. Okay, so let's just go through this very simple argument for why it has to be the case a lot of times, pretty much in all practical situations you encounter with a variable continuous, we're going to have this these variables be linearly independent. So let's suppose not. Suppose that the null space of XG was not just the set containing the zero vector. Then I'm going to have a variable, so there's going to be some j. I said I. Then there's some I. There's some variable I. Such that I can write xi as a linear combination of the rest. I guess I call it cj xj. For all j that are in that correlation set except I. All right, that's just the definition of linear dependence. And these cj's are not all zero. Okay, so nothing fancy so far. But now let's remember what the KPT conditions are. The KPT conditions tell us that xj transpose the residual is equal to lambda times sj for all j. Right, so let's just take an inner product of the residual on both sides here. So if I take an inner product with the residual, both sides, and I remember the KPT conditions, I get xi transpose y minus x beta hat here. That gives me si times lambda. Right? And here I get cj times sj times lambda. Right? Nothing tricky. And I'm going to cancel out the lambdas now, assuming the lambda is positive, because we're talking about the lasso and not least squares. So we're going to say that the tuning parameter value is positive. And I'm just going to multiply both sides by sj. And that tells me that the sum of, or multiply both sides by si, excuse me, si times sj times cj is equal to 1. And I call this ai, or aj in the notes. So what does that mean? It means that I've now shown that if the null space is not trivial, then I can take si times xi, so I can take xi, perhaps flip its sign, and I can write that as the sum of si times sj times cj times sj xj. So remember, this just came from that first equation. I just multiplied both sides by si, and I multiplied by sj twice here. So this is just the same statement. It's saying that I can take xi and represent it as a linear combination of the rest. Just change that slightly. And I said that I can represent si xi as a linear combination of sj xj, where these weights, ai, right, remember this was aj, have the property with that they sum to 1. This is a very special type of dependence. We've actually said that that si, in other words, si xi, it lies in the affine span of sj xj. already we should be thinking that we've shown something that's informative here. Because let's suppose that I lay down a bunch of variables. Let's suppose I lay down k variables. Their affine span is k plus one dimensional, right? And for another variable to be contained in that affine span, if that k plus one dimensional is a proper subspace of Rn, say, that's going to happen with probability 0 if the variables have a continuous probability distribution. Right? If I lay down, think about I am in Rn, and I pick k variables, and I look at their affine span in some subspace, and it's k plus one dimensional. Then, for another variable to be contained in this k plus one dimensional subspace, if this is a proper subspace of Rn, it's going to happen with a probability 0. Even if those variables are highly correlated, it doesn't matter. This is a set of measure 0 in Rn. Okay, so if the variables have a continuous probability distribution, we're going to have that I can take one of the variables and represent it as an element of the affine span of the rest with probability 0. That's only not going to be the case if I collect enough variables to make this affine span be all of Rn. Okay, so I just said something that I tried to reason with you why this doesn't happen very often on your homework, which I think we're going to release today, or that's the plan at least. You're going to actually prove that if x1 through xp have a continuous probability distribution, and this happens with probability 0. You guys are basically going to you're going to check the intuition I just conveyed, which is that this can happen with probability 0 if the variables have a continuous probability distribution, in which case the lossy solution is always 0. All right, just a little bit of lingo because you'll see it on the homework, and I'll tell you as well. And you'll see this in a lot of papers that have to do with high-dimensional regression. We say that a set of vectors x1 through xp in Rn are in general position provided that basically this can't happen. That's all it means. Is that if you give me any subset of variables and you pick any signs, I can't have that one of them is exactly the affine span of the rest, provided that I don't collect more than n variables, right? N or p variables. If I collect few enough variables, this can't happen. So their general position, provided that this can't happen, for any subset of size k, where k is less than both n and p. All right. So there's a more rigorous definition in the notes, but this is all really that it means.
Does this mean that this lasso is consistent only when the dimension of the data is less than the number of data points?
No, it doesn't. And by the way, consistency has nothing to do with this. We're just talking about uniqueness.
Yeah,
So-
I mean, if it is unique, then
No, so what you're going to prove is that if p is, anything compared to n, doesn't matter. As long as p is finite, n is finite, if the variables have a continuous probability distribution, they can be as correlated as you want, then this can happen. With probability 0, this happens. So the lasso solution is unique to probability 1. In other words, if the lasso, the non-random deterministic statement is that if the variables are in what we call general position, I'll write that down just so that we have it in our mind. If the variables are in general position, then the lasso solution is unique. That's the deterministic statement.
So by general position, you mean k should be less than of n.
So what it means is that if you give me any subset of k variables, then I cannot express, suppose I take their affine span, then I can't find another variable that lies in that affine span besides the ones that we're used to create. So maybe I'll make that a little bit more precise.
It doesn't mean, I think it doesn't mean that the design matrix, right?
No. In fact, it can be
Wouldn't have.
greatly rank efficient. So let me just write down that statement. If the variables x1 through xp are in general position, then the lasso solution is unique. For all values of the tuning parameter that are positive. So how do we show that? Well, we showed that basically if they're in general position, then this can happen. Because by definition of general position, this can happen. And that means that the null space has to be only the vector containing 0, which from here we know that basically that means that there's only a unique solution, and it's given by taking A equals 0. That was the sequence of arguments we gave that. What does general position mean? I can rewrite it in a different form. Maybe it's easier to not think about variables. If I take any subspace L, it's in Rn, and it has dimension k, which is less than n p strictly. This can only contain at most k plus 1 elements of the set x1 through xp. Okay, actually, just for a technicality, we say it can only contain at most k plus 1 elements of, if I take plus or minus x1 all the way through plus or minus xp. Okay, where I'm allowed to take for each one of these an arbitrary sign. So now you can see why it's not going to happen with the continuous probability distribution, right? Lay down an arbitrary subspace in Rn. That's going to have measure 0. So if my probability distribution is continuous, the probability of more than k plus 1 elements lying in that subspace is going to be 0. Okay, so basically, the lasso solution is pretty much always unique unless we have discrete data points. If we have predictor variables that are discrete, like if they all take values 0 or 1, or they're mixed, continuous, and discrete, then we can have non-uniqueness in the solutions. That's a pretty favorable result, but even when they have non-uniqueness, we still have this property that interpretation of the signs of the non-zero coefficients is consistent across whatever solutions are. Okay, so there were no fancy arguments here. We didn't have to make any asymptotic statements. There was nothing really that was difficult. It just came right from looking at the KPT conditions and playing with them to get that form, and then playing with them to see what happens if we have a correlation set was ranked efficient, and so on and so forth. And so I wanted to give you an example of this argument, this nice example of using the KPT conditions to get something. Are there any questions about what we just showed? you're going to verify a few claims about general position. Like I said, you're going to prove that if you have a continuous probability distribution, then for x1 through xp, then they're in general position with probability 1. And you're also going to extend this argument to the following problem. So if I'm actually interested in L1 penalized estimation, where I replace the least squares loss by a function f that's strictly convex and differentiable, then actually we get the exact same results with the same set of arguments. So you're going to recreate the arguments we just did today in lecture, and then take a look at the lecture notes if you missed anything for this problem. Which means that if you're doing L1 penalized logistic regression, L1 penalized Poisson regression, whatever, anything like that, the solution is unique as long as the columns of the predictor matrix are in general position. And if you measure the predictors from a continuous distribution, the solution is unique with probability 1. So this might be surprising to somebody who only does optimization and does not have a knowledge of statistics, because this is not a strictly convex criterion. So from a purely optimization perspective, that's somewhat of a surprising statement. So you'll do that one on the homework. Okay. So now I want to go through some theory for the lasso, unless anybody has questions.
It would be great if you can also comment on consistency and consistency.
That's what we're about to do. Yeah, we basically just shown some basic properties. Shown the lasso solution is pretty much always unique, so we don't have to worry about that one. And now we'll go through some theory. Okay. So I'm going to remind you what we saw for best subset selection also, because you're going to see a similar rate popping up. Remember, we saw that if I looked at the best subset selection estimate, which I defined as the solution of this problem, so I get out beta hat, I guess I'll call it beta hat subset, differentiate it from the lasso solution. Then we showed that if lambda is, I don't remember what the order of lambda was, it was like maybe about log p or something like that. Yeah, lambda was like log p. So it's on the order of sigma squared log p. Then, and also remember, we're in the setting where we think that y is equal to x beta naught plus error, where the errors have marginal variance sigma squared, they're independent, and this, so we have a true underlying linear model, and the support of this underlying coefficient vector beta naught was s, and its size was little s naught. So if we're doing variable selection, we're a truly sparse underlying linear model. We use best subset selection, that value of the tuning parameter. Then we prove that the risk inflation of the best subset selection estimate, so the difference in the fitted value from subset selection to the true mean, is less than or equal to, I think it was like 4 log p plus other terms, but that was the rate, log p. And this was true actually over predictors and underlying coefficient vectors. And so the expectation here is taken into that towards the coefficient vector beta naught. And we saw that furthermore, if I looked at any estimator, I'll call it beta tilde, then the lower bound for this quantity, the worst case, excuse me, I'm sorry, I forgot that the factor here is sigma squared times S naught. So this is the ratio of the risk of the best subset selection estimator to the oracle risk. The oracle just performs least squares on S, and his or her risk, depending on whether you think the oracle is a guy or a girl, is S naught. Okay, so that's the risk inflation with respect to the oracle risk. And the worst case risk over the best estimator is lower bounded by log p. That was another result that we had cited, didn't prove, but it came from a kind of a famous paper from the early 90s. Okay, so I'm probably forgetting some the constants here, but that was the punchline. Okay. How about the lasso? What can the lasso give us? Well, there's a ton of theory for the lasso in terms of convergence rates. And so I tried to summarize some of the main results in one page. That's on page 10 of the notes. And we assume the same linear model setup. Here we're going to assume the same sparse underlying linear model. But we're going to think about various cases to consider. So the first case is what I don't know if I call it in the notes, but sometimes it's called, yeah, I didn't write this in the notes, but sometimes in the literature you hear these called slow rates. In the notes I call it the basic result. We have to make one kind of pretty innocuous assumption on x, which is that we assume that the columns of x all have norm equal to n. Excuse me. That scaling actually ends up being important. So you can see there's already an assumption on x, but it's really not that steep at this point. So the slow rates, they don't assume anything on x beyond that. They assume that the predictors can be as correlated as you want. So x is arbitrary beyond that. And the if I take the lasso estimator and I look at the loss in fitting the mean of y, then this is average now across all inputs. That's why I have 1 over n times the L2 norm of x beta hat minus x beta naught. This is converging from probability at the rate to 0, at the rate let's put it here, root log p over n times the L1 norm of beta naught. Okay, so that's a famous rate. I think probably the first paper where this rate appeared was in 2004. And it was a fairly sophisticated proof at that point. Since then, people have gone through this several times. Now the proof of this result is like 6 lines. And I gave you a reference in the book. Now that you know concentration and measure, that's the only difficult part, is a concentration and measure argument. Everything else is very simple. And that doesn't use the KKT conditions. Okay, all we do is we take the lasso criterion. I'll give it to you in words because we don't have time to prove it. You take the lasso criterion, and I say that if I plug in beta naught here, the true coefficient vector, this must have a larger criterion value than lasso solution. Right, so lasso solution was made to be optimal for this criterion value. So this evaluated at beta hat is less than or equal to this evaluated at beta naught. Then I rearrange that to get a statement on this difference. I can actually expand the squares and rearrange that to get a statement on this difference. And it ends up looking like we can bound it using like then a Cauchy-Schwarz argument by something to do with the one norm of the true coefficient vector, that's where this comes from, times a Gaussian random process that has to do with this error, the error term up there. Epsilon. After I plug in y is equal to x beta naught plus epsilon. And we use a simple concentration and measure argument so that that process doesn't grow larger than this, root log P over n. And that gives us the basic result. Okay? So let's take just a quick look at how that compares to that guy. Well, we can already see that we're not very close to that bound. Right? Because I multiplied both sides by n, I get root n log p, about a lot bigger than log p. And I have this factor. This is not to do with this is not the L0 norm of beta naught. The L0 norm of beta naught would be S0. It's the L1 norm of beta naught. So actually it's a lot bigger than that if the true coefficients get larger. Okay, so we're pretty far from that risk inflation bound of log p. But we still get consistency provided that consistency provided the one norm of the true coefficient vector is growing slower than n over root n over log p. Okay? And I should tell you, by the way, that we have to choose a particular lambda to achieve this, and I think it's like sigma root log p. Oh, okay. Thanks. Okay, so that's what I would call the slow rate result, or we also call it the basic result sometimes in the literature. Like I said, it's a very easy thing to prove, so that's the nice thing about it. How do we get fast rates? Well, if we could get fast rates that rival rates like that, without any conditions on x, then we'd be in a great situation. We'd be basically, at least as far as that rate is concerned, we'd have completely circumvented the need to use subset selection, which is NP hard and lasso is very easy to solve. Unfortunately, that's not the case. We can't just get this fast rate for an arbitrary x. And in fact, there are theoretical results that show that that's not possible. So it's not only speculation, there actually are results that show that it's not possible to get that rate for arbitrary correlation patterns among the predictive variables. However, we can put conditions on the predictive variables that control the amount of correlation they have, and we can get a rate that looks like that optimal rate that's achieved by best subset selection. And so that's what I call fast rates. And I'll just tell you the result first. And I'll tell you the name of the condition that we use. If x satisfies what we call the compatibility condition, compatibility condition, then for the same choice of lambda, I believe, sigma root n log p, we get 1 over n times x beta hat minus x beta naught squared being equal to something that's on the order of, now it's log p over n, not root log p over n, times, it's got to be a factor of s naught in the numerator, sigma squared s naught over this thing called the compatibility constant. So it satisfies the compatibility condition with constant E0 squared. Okay, now let's rearrange this quickly and just let's think about what the ratio of this loss is going to be to the oracle's loss. It's going to tell us that x beta hat minus x beta naught squared over sigma squared s naught is like on the order of log p. We still divide by this compatibility constant, but that's taken usually to be a constant. So we've just shown that if x satisfies something called the compatibility condition, we get the fast rate achieved by best subset selection. There are no restrictions here on beta naught. Okay, we're not saying that beta naught has to satisfy anything in particular. It's just that the predictors can't be too close. So that's a good result for last time. Okay. What is the compatibility condition? Well, that's something that I would call, it's the thing you need to prove the result. You try to prove this result. So you start with the same sequence of arguments. I plug in beta naught into the Lasso criterion. I say it's bigger than or equal to beta hat. I rearrange. And then I realize there's something I need to prove this result to get this rate log p. And I enforce that on x. It's not at all natural. There are lots of things that are kind of weakly equivalent to it that are more or less natural. But that compatibility itself is not that natural. I'll write it down for you. But the best we can say about it, if we look at it for a second, is that it requires x to have only a kind of a mild form of correlation between its columns. So the compatibility condition with constant E0 means that if I take 1 over n times x beta squared, it has to be bigger than or equal to E0 squared over S0 times the 1 norm of beta S1 squared for all vectors beta such that let's try to digest that. S here is the true support set. That was the support set of the underlying variables beta naught. S0 was its size. So this says that if I look at all vectors that are weakly sparse, which means that on the non-truly active variables, they can't have too big one norm, and bounded by the one norm on the active variables times 3. They're kind of weakly sparse. These vectors are mostly concentrated on the active variables. And I look at the L2 norm squared of x times beta, then it's bounded below by something. So first, let's look at this. If beta only was non-zero, and the components that correspond to s, then this would look like xs. Well, first, let's write xs beta s squared. That's what happens if beta is only non-zero in the s components. And its L2 norm is going to look like beta s transpose xs transpose beta s. I'm saying this has to be bounded below by something that looks like a norm of beta s. So it's roughly an eigenvalue, a lower bounding eigenvalue of xs transpose xs. That's a kind of very rough sketch for what it looks like. And what does it mean to lower bound the eigenvalue of xs transpose xs? It means that the predictor variables that corresponds to the truly active variables cannot be too correlated. They have an eigenvalue, the lowest eigenvalue is found in the latent. Not too much correlation present among the truly active. That's not exactly what it's saying, right? Because the beta can be weakly sparse, and here I'm actually using a 1 norm instead of a 2 norm. So it's a little bit funky. That's why I say it's the thing you need to prove the result. So this is exactly what you need to prove that result. Okay, but there are other conditions that are kind of weakly equivalent to this that look like restricted eigenvalue conditions. And I wrote down one of them, the bullet point below. Yeah, I understand.
How does this compatibility constant scales in the random design case with this sparsity coming to S norm?
Good question. The compatibility constant, I think, is truly a constant in that case.
Truly constant?
Yeah.
Wouldn't that depend on something like log S?
Oh, this S.
Yeah. Yeah.
I don't know, actually.
I think for the similar definition, people use like incoherence condition, the thing is bounded about by a constant times log sparsity.
That could be, yeah. But I guess if we're assuming, right, that S doesn't grow, then this whole thing acts like a constant. Yeah. Yes, Yusheng alluded to kind of a common extension, which is that how do you know if your predictors satisfy this? Well, you don't always know that, but you could take a stance where you say that if my predictors were themselves random and came from a random ensemble, then I could try to prove this happens with high probability. People do that a lot. It's very common. And so the random Gaussian design is a common case that people study. And this condition, as well as the restricted eigenvalue condition that are down below, they both occur with high probability over that random design.
Wait, so the argument is that if that happens with high probability randomly, then your data is likely to happen? Or?
Okay, that's also a good question. That's not really the argument. So this is getting into maybe, how much time do we have? I don't want to say too much about this because I didn't want to go through the final dual witness construction. But essentially what happens is that there are two camps of people. There are camps of people who, maybe I shouldn't make such a strong statement. There are camps of people who consider data as given, and they don't want to place restrictions on correlation and predictive variables. I think that's unreasonable. And so those people would cite things like this slow rate, where there's nothing that really enforces correlation balance among my predictors. And I know that's consistent only as long as the true coefficients don't grow too large and not too fast. Then there are another kind of group of researchers, and it's not that they believe that the data they observe truly has correlation that's bounded, but rather that if they could design experiments themselves, they could design them in a way where the predictor measurements would be taken to be random Gaussian, and therefore I know it's going to happen. That this compatibility condition is achieved, and therefore I know that the lossless solution is a good thing to use. And so that's getting into compressed sensing, where I can actually choose the design of my experiment, and it's not something beyond my control. So it really wasn't like a very, I didn't make a very strong statement there about philosophy. I meant to say there are different types of settings in which you apply these results. Some where the observations are given to you and some where you can design them.
So then I had a third camp of people, which is me, which is I claim there's no real data set for all of this conditional error, except
It will certainly hold for certain parameter, which wouldn't necessarily be a constant. It will hold for some deterministic parameter.
well, yeah, right, but for it to be useful.
So if you can estimate that for any real data set.
It's not a check, it's not an estimable quantity, and it's not a checkable condition.
All right, let's
I think it's useful for theory.
yeah. So engineers can design experiments, right? If I was an engineer, maybe I can choose what I'm actually going to measure. I might, if I choose my measurements to be random Gaussian, I get this, I'm happy. What Larry's saying is that outside of that, if you're in a situation where you're subject to someone else's design or nature's design that I don't know it's going to hold, in which case I should be skeptical about applying a theoretical result like this one, whereas we have other results like this one that don't assume stuff about the correlation of predictors. And there are other, by the way, there's lots of other theory that doesn't assume anything about x. Like when we talk about degrees of freedom, there's no assumptions whatsoever on x. Okay, so we don't have to always live in a world where we think that we're subject to some nice constraints on how correlated the predictors are. Okay, let's take a short break and then when we get back, I'm going to do the prime multiple witness construction, which I think is interesting. I can't see the person's answer me. I can't see him. Maybe he's not. Oh, there he is. Jersey. Okay. I just told you a joke. Okay, here's one interesting tip that I wanted to say actually, that this falls off what we just said. There are a bunch of conditions like compatibility, restricted eigenvalue conditions, restricted isometry property, coherence. These things are all very similar. And so there's one paper by Sarah Vandegeer and Peter Buhlmann that links these all together. These are all conditions that people use to prove fast rates with lasso. Some people say, no, I don't like compatibility. I like restricted eigenvalue because it feels weaker to me. And I get the same rate. And a bunch of other stuff like that. Well, they're all very, very similar, and they're all kind of more or less equivalent. So if you see all these conditions, you can think like, well, they're pretty much equivalent. They are less strong than what we're about to impose right now, because we're about to do something where we want more than just a good rate from the estimation error. We want to actually recover the true set of underlying variables. So these are even stronger conditions than those. I think, although I could be wrong, the last time I checked, we do not know of arbitrarily large deterministic designs that satisfy something like the restricted eigenvalue condition. The only way we can ensure that that kind of condition holds for arbitrarily large designs is by through some kind of random mechanism, like a random Gaussian design. We can show that it holds with high probability. That may have changed. Somebody may have found an example, but I'm not aware of it. So, somebody correct me.
The whole theory for lasso lies on that the noise is Gaussian, right? And I presume that's because we are taking L2 objective.
So the noise doesn't have to be Gaussian actually. It has to have sub-Gaussian terms. So it has to kind of die away just as fast as a Gaussian.
But is it if we require that property, is it because we are taking L2 objective?
I mean, that's used for a lot of the concentration and measure arguments. I'm not sure if well actually we saw some interesting papers in our reading group recently where the L2 objective was pitted against something like an L1 objective, and I think that's probably a current topic of research. I know people do have theory for what happens if they have an L1 objective and an L1 penalty.
Yeah, because I don't think that will work if we have an L1 objective.
No, the LAD lasso, that's what people call the LAD lasso, least absolute deviation for the loss. That is studied. And so we do have rates for that. But how it compares directly against the L2 loss, I'm not sure. Yeah, any kind of twist that we think of, change the loss, change the penalty, like it's been pretty much done. That's kind of an exaggeration, but this is a very active topic of research, so you can look up like tons of variants of these results. Okay, so we're going to go for support recovery now. And I'm going to try to, in the last 20 minutes, give you an idea of how this is proved. So we went for good estimation error, like x beta hat should be close to x beta. Now we're going to try to go for support recovery. So we have the same underlying model. And S is the support of beta naught. And we're going to want a lasso solution beta hat such that the support of beta hat is exactly equal to S with high probability. first came out, I think were very surprising to people, that you could actually achieve such a thing. And they still are surprising if you can do simple examples that meet the conditions that we're about to put down. And you'll see that large enough examples, you can get exact support recovery with elastic. Kind of a surprising fact, although the conditions are fairly stringent. And we don't want only that, we also want that the sign of the active variables, that the lasso estimates, is equal to the sign of the underlying variables as well. So this is often called sign support recovery. So how do we do this? Well, there are a bunch of papers that prove such claims like this. I'm going to focus on one method that's called the primal dual witness construction, because I think it's a pretty neat use again of the KKT conditions. And also, it gives you an idea of how you might do this for other problems besides the last one. Because it's kind of a general technique for doing so. And it came from a paper by Martin Wainwright in 2009. So I gave the reference there. You can take a look at that paper for more information. Okay. I'm going to say in words what we do first before I go through the math. What we do essentially is we plug in S as the support of the lasso solution into the KKT conditions, and we see what implications that have. We want to make sure that whatever the solution is, it has support S. The KKT conditions are the defining set of equations for the solution. So we see what happens in the KKT conditions if I force the support to be S. That has a bunch of implications, and we want to make sure that those are all verified. So if we can verify that the KKT conditions hold when I plug in S to them, then we prove that the solution is going to have support S. So really all we're doing is, like I said, we're plugging in what we want the KKT conditions. We're verifying that that set of equations is consistent, it can hold, and then we're saying, okay, that characterizes the solution, and therefore the solution has that property that we want. So we take the KKT conditions and we break it up over two sets, over S and S complement. Similar to what we did earlier with the correlation set. Really, it has the same structure. Kind of unfortunate use of the double S there. This is a subgradient, and this S is the set. So hopefully that's not too confusing. Maybe I'll call the subgradient Z. Just doesn't confuse us. So those are the KKT conditions. I haven't done anything yet that's at all unusual. I've just written them in two blocks. Now I'm going to suppose that the true solution, suppose that it is the case that the support of beta hat is S. Well, then I know I can, in here, I can write this as XS beta hat S, right? And I'm also going to suppose that not only is that true, but the subgradient over the S variable is equal to the sign of the true coefficient that are non-zero. Here I should have said S. Okay, so that here I could plug in the true sign. Well, this completely characterizes what beta hat has to be. Right? We saw that already with the previous arguments. I get an explicit expression for beta hat S here. So if I were to tell you that the support was S and the signs were this, the KKT conditions, it tells you what the loss solution has to be over those components. So I'm going to rearrange that equation and solve for beta hat S. And I'll do it right over here. It just is the same thing we did before. I get that beta hat S has to be, and I'm going to assume here actually that I'm going to assume that XS is full column length. look, this is a statement about the true model. That in the true model, the ones that are non-zero correspond to linearly independent variables. So using that, I can just solve this first block for beta hat s, and I get there's an explicit expression for the Lasso solution over those non-zero points. And now what I want to check is that if that were the Lasso solution, the KKT conditions would be satisfied. Well, how are they satisfied? The first one is satisfied by construction, right? There's no problem with that. I just chose beta hat as one equation. But I have to satisfy this. And how do I satisfy that part? Well, for that part to be satisfied, it has to be the case that this is a proper subgradient. So it has to be the case that Z minus S is really a subgradient of the one norm of beta hat evaluated at minus S. Well, what is that? That's just zero, right? So it has to be the case, in other words, that every component of Z minus S is between 1 and minus 1. So if I can check that's true, then that satisfies the KKT conditions. So let's solve for ZS now, right? Because look, ZS is defined in terms of beta hat S. This has already been determined. So I can do that. And I get that ZS is equal to 1 over lambda times x minus s transpose y minus xs beta hat s. And remember, we've determined beta hat s already, so I'm going to go ahead and plug that in. Okay, all I did was just solve for ZS, and I'm going to just rewrite that slightly. I minus all this PS. This is the projection onto the column space spanned by the truly active variables xs times y. And I get a 1 over lambda here. And then this term I get just plus xs. That's supposed to be closed out. No, I guess there's no x. Am I missing something? XS transpose. Maybe I had an XS transpose out front here. Is that right from the notes? Oh, minus S. Thank you. Yeah. Right. Plus x minus s transpose xs xs transpose xs inverse xs. I think that's the right expression. Yeah, I think in the notes I must have missed this factor for xs, because that definitely has to be here. So that's the right expression. So, look, this determines the subgradient over the rest of the variables. So, if I can prove that this is less than or equal to 1 in every component, then I've satisfied the KKT conditions, right? I just plugged in what I want to and shown that they hold. And therefore, the solution has to have the property that supports S. One more thing, if I can also show that, so if this is true, then beta hat is really a solution with support beta hat equals S. That's what we wanted. Okay, so that's how we show that the solution has the right support. Furthermore, if I can show that the sign of beta hat I have to show actually, right, well, I shouldn't have been so quick here. I have to show that's true. What else are needed to verify the KPT conditions? One other thing, I have to actually know that this is equal to the sign of the variables over the S set. Right? I verify this is a proper subgradient because it has norm less, it has algebra less than equal to 1. For this to be a proper subgradient, it has to have the right signs, the signs that match the signs of the components of beta hat. And so I need to verify that the sign of beta hat S is equal to SS, ZS. So if these two things are true, then it's the solution with support equals the true support, and with signs equal to the true signs. Let's take a look at this real quick. This is deterministic. Nothing here is random in this part. This is what's given to us. Remember we said that we're going to plug in the true signs here. X is not random here, S is the true support. This part's entirely deterministic. So we're going to need some condition on X and S to make sure this doesn't get too big. Right, because we have to save between -1 and 1. This is random, this part is random. It's like, well, I can even keep going here. Why is X beta naught plus S? What happens if I project X beta naught onto the space spanned by the variables orthogonal, all the variables into the space is orthogonal to the truly active variables? I get 0, right? Because X beta naught S is the same thing as XS times beta naught S. So this only becomes the error, that's all that's left. And so this part is now, it's a Gaussian process like we've seen before, and we want to kind of control how big it is. So I can make an argument that this is going to happen with high probability, provided that I place some kind of conditions on how big this can get. That's the condition that we actually end up needing. That's the first one I have in the notes. We control how big this gets by looking at kind of the standard computation measure argument. How about this thing? We want to now prove that the sign of the solution over the active variables is equal to the true signs. Again, I go ahead and I plug in y equals x beta naught plus error. And I get that that condition is equivalent to the following property. Once I just plug that in and do a little bit of rearranging, it's equivalent to the sign of the ith true coefficient plus some random perturbation delta I remains equal to its original sign for all of the truly active coefficients, where this delta, you can guess what it is just from looking at the form of the Lasso solution, but I'll tell you what it is. It's just ends up being XS transpose XS inverse XS transpose epsilon minus lambda times the vector of the true signs. And I just take the ith component of this guy. So how am I going to make sure this is verified? So far we saw we have to have conditions on X and S to make sure that one's verified. That's a Gaussian process argument. I want to make sure this one's verified. For this one to be verified, we need to make this small, but also make sure that this is going to be big in absolute value. Right? It's actually a relative statement. I need to make sure that this is big enough away from 0 to begin with, that when I make a random perturbation, the sign still stays unchanged. So the kind of statement that we end up placing at the end of the day to make sure this is true is actually a statement that says that the true coefficients are large in magnitude. That's a new kind of restriction that we didn't need in the previous set of results. We only need it for support recovery. And it makes sense intuitively, right? If you're telling me you're going to recover the set of truly active variables in the underlying linear model, they better have big coefficients. If they have small coefficients, I can very well miss them for support recovery purposes. If I was just doing estimation error, missing them is not such a big deal, right? Because a small coefficient means that it probably contributes a very small amount to the fit. But for support recovery, it is a big deal, and so we need the non-zero coefficients to be substantially far away from 0 that when I add this random perturbation, again, this looks like a Gaussian process. That doesn't flip the sign. Yeah.
How do you get this?
This, I just took the, so see, I have sine of beta s must be equal to the true sine square. See, s is the true sine. I just went up there to the form of beta s. That's the Lasso solution from the KPT conditions. And I plugged in y equals x beta naught plus epsilon. And I just got this from a bit of rearrangement. That's it. So in summary, let me write down the primal Leibniz construction in summary so that you can see what we just did. The first thing we do is that we solve for the Lasso solution, assuming that has support S in sines beta naught S. So the sines, yeah, sine beta naught S. So assume the things you want, solve for what the Lasso solution has to be from the KPT conditions. 2 is that I have to solve for the subgradient over the non-active component ZS. And then 3, I have to verify that I have a proper subgradient in order for the KKT conditions to hold. I have to have a proper subgradient, right, that's paired with this proposed solution. If I can pass this step, then I have a solution with the desired property. Proper subgradient means, number 1, that on the inactive components, they're all less than or equal to -1. I can do whatever I want because there's 0 there. And on the active components, they have to match the signs of the solution. So I need to make sure, right, that this is equal to CS, which I'm assuming is equal to the sine of the true coefficient. So that's the steps to the primal Leibniz construction. The word dual is really used in kind of a funny way here. It really should be called the primal subgradient Leibniz construction. But people in optimization often think of subgradients as dual variables. And I have a little blurb at the end of the lecture notes as to why you might think that. But the thing to takeaway point is plug in what you want with KPT conditions, see what that implies, check that that holds, and therefore you get what you want. It's also nice that it gives us a converse. If we actually plug in the support and the signs, and we solve the subgradient, and it so happened that this didn't hold, like this was bigger than 1, and we know that there is not a Lasso solution that recovers the set S, and that is something to this. Because the KPT conditions are necessary and sufficient. They go both directions. So it gives us both a way to prove that it happens and a way to prove that it doesn't happen. And the rest is in the details, spelling out that these conditions actually happen using some concentration and measure arguments. And I have some details in the notes so you can see the exact conditions that we impose.
This is exactly the Lagrange view of the constructed view optimization by introducing a constraint by replacing this x beta minus y.
The subgradient.
Yeah.
Yeah, right. So you can.
That might be why they call it the view.
I don't think that's why in general, but in this case, yeah. If I can construct a dual problem, which this is actually the scaled dual variable. The dual variable ends up looking like this times lambda. I think in general, the association between subgradients and dual variables comes from just the representation of subgradients as the argmax of, like the subgradient of the 1 norm is a set of all vectors that is to have an infinity norm less than or equal to 1 to maximize the inner product with that vector. I think of that as an optimization problem, so these guys are the solutions to that. But yeah, you're right. In this problem, I can actually think of it as a dual variable to a Lasso variable. Okay, hopefully that wasn't too rushed and you guys got the gist of it. Next week we'll do bootstrap.